Hi everyone, welcome to the video. Today we are going to solve the problem trapping rainwater. In this problem, we are given an array and every element of an array is basically a block with some height. For example, if you can see here, the first element is a block of height 3, then this element is a block of height 2, and then this element is a block of height 4. Other elements are of heights 0. And what we have to return is the maximum rainwater that can be trapped between these blocks. We are going to solve this problem today. We won't directly jump to the solution, but we will try to gradually build and see how to reach the solution. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's start. To begin with, let's first note down a key things given in the question. We are given an array. The size of array is n. All the elements in array are non-negative and all the elements represent height of blocks. Width of each block is 1 and we are asked how much water can be trapped. If we consider an example, here this block has height 3, this block has height 2 and this block has height 4 and rest all blocks have height 0. In this case, the total water trapped is equal to 10. 3 plus 3 plus 1 plus 3. How does this come up? We will discuss this later. So if we have to see that if our solution is a black box, then we are getting input as an array and its size, and we have to return an integer which is water trapped. So our function signature would look something like this. Before jumping to the solution, let us first try to visualize how the water will get trapped. So this is a visual representation of the example that we have taken. These are the blocks of heights 3, 2 and 4, and the below ones are of height 0. Now let's see, if it rains over this, how much water will it be able to trap? The first block will not be able to hold any water because water over it will overflow down. Then the second block will be able to hold water only till this height because anything above that will overflow. Similarly for this block. For this block, it can also hold some water which is up to this height and not beyond this because that will overflow. And similarly for this block too, right? To calculate, this block is holding 3 units of water. Same with this one. This block is holding 1 unit of water. 3 is the total height and 2 is the block height. So it is holding only 1 unit. And this block is again holding 3 units of water. So the total water that it could have been trapped was 10. Now what are some observations that we can make? First thing that we can see is that the answer for the whole array depends on the answer for individual elements. So if we compute the answer for individual elements, that how much water can individual element hold, and sum that up, we will get the answer for the whole array. This is the first observation. Now second thing is, how do we get the water held by one single element? So if we consider one single element, the water held by it will be dependent on what is the maximum left height to it, what is the maximum right height to it, and its own height. Why do we say that? For example, consider this element. The water held by this element is not just dependent on what is the height of the just immediate left bar to it, or what is the height of the immediate right block to it. It is dependent on that, okay, the left maximum I can reach is level 3 and the right maximum I can reach is level 4. But it's not that I will be able to store the water till level 4. Why? Because if I go anything above height 3, it will overflow. Therefore, to get the water stored by one element, we can have the left max height and right max height, and we get the minimum of the two. Consider, for example, if there was a bar of height 5 here. Now how would the water stored would have changed? In that case, each of these elements would be able to store water till 4 level, because this bar would be able to support till level 4. That is why the water stored at every element is basically minimum of left max height and right max height. Also, we will have to subtract its own height from this minimum of the two to get the water stored. For example, consider this element 2. Here it could store till level 3, but its own height is 2. Therefore, the water stored by this is 1. So what does our overall approach to this problem look like? We are definitely going to iterate. Now in every iteration, we will calculate the water stored by that particular element. And then we will finally sum all of this. Now how do we calculate water stored for every particular element? For that we need 3 things: left max, right max and own height. We know own height, that is AI. But we need to be able to calculate what is the element maximum to its left and what is the element maximum to its right. So this is our sub problem that we need to focus on. Let us now focus on calculation of left max and right max for an array. This is a very common sub problem that we have to use in multiple questions. We will here focus on the calculation of left max, and calculation of right max should be pretty similar. Now, what is left max for any element? Left max for any element is the maximum element which is to the left of it. Consider this. How do we calculate left max for this? We go and look at every element to the left of it. We note down the maximum value and we will say that this is the left max for this, right? If our aim is to calculate the left max including the current element, we can include it. And if our aim is to calculate excluding the current element, we can exclude it. In our problem, we will calculate the left max by including the current element. So the left max for 2 will be dictated by the maximum value among all these elements. Now here we calculated the left max only for one element. But what if we have to calculate the left max for all elements and let's say store them somewhere? So where will we store it? We can store them in an array, right? And how will we do it? Like the same way we did it for 2. For every element, we will move towards its left and we'll note the maximum value. And this we will do it for every element. So what will be the time complexity in this way? The time complexity will be big O of n square. Why? Because we will have to iterate for every element, and for every element we have to traverse back to the left till the start of the array. So big O of n multiplied by big O of n, the time complexity becomes big O of n square. But is this efficient? Let's see. Let's say this was an array and I have done my all calculation for this element. So this means for this element I have gone and scanned through all the elements in the array to its left and found that there is some maximum value which is the left max for this element, right? Now if I have to calculate the left max for this element, do I really need to go through each of these elements again and find the maximum value? Or I can just see that, hey, I already know what is the maximum value among all of this, and I can just compare it with the current value. And if the maximum is greater than current, that means even for this element, the left max will be equal to this. While if the current is greater than the maximum, then the left max for this element will be equal to current. So can we not say that left max at I is equal to maximum of left max at I minus 1 comma AI? That means if I know the left max at 0, I can calculate the left max at 1. If I know the left max at 1, I can calculate the left max at 2 and so on. Therefore, as I iterate over the array, I can keep filling the left max values. Let's see. Here, left max at 0 will be equal to 3 because this is the first element and this is the maximum value. And if we now start filling the next elements based on this and the current element, we can find that the left max for this is also 3, 3, 3, 3, and this is now 4. Right? Let us say, just for hypothetical example's sake, this element was 5 instead of 2. If this was 5, then the left max here would have been 5, and even for this element we'll see that the left max is 5 and this also is 5. Now, what does our approach to calculate left max look like? We first declare the left max array in which we will store the left max for every element. First of all, we fill the left max of 0, which is nothing but a of 0, and then we iterate. In every iteration, what all do we have? We have ai, which is the current element. We also have left max of I minus 1. We compare the two and accordingly fill the left max of I. And that is how we can fill the whole left max array. Similarly, we will be able to do for right max. And for right max, this formula will instead depend on I plus 1, right max of I plus 1. And we will be iterating from right to left. Now this reduces our time complexity to big O of n because we are iterating only once. And it also gives us space complexity of big O of n because we are storing all the results in a left max array. One thing to note here is that in our original problem, trapping rainwater, we don't actually have to return a left max array. What we have to do is use the left max for every element. Now, if we see here in the algorithm, to calculate left max for any element, all we need is left max of the previous element. We don't need the whole array. Therefore, instead of this array, we could use just a previous element variable and store the left max of previous element in a variable, calculate the current element left max from it, and then our current element left max will become the previous left max for the next iteration. And that way we will be saving on the space complexity as well, since we don't actually have to return the left max array, but we only have to use the results for each of these elements. So our modified algorithm would simply look like this. Instead of left max I minus 1, we will have something in this previous variable, and here we will compute a current, and now our new previous will become the current. Let us now try to apply our learnings to the main problem. So how will we approach the solution of this problem? We can iterate, and in every iteration we will be calculating the water stored by element using this formula. So for this we need a left max, a right max, and its own height. As we can see from our previous learning that we can calculate left max using the variables like previous and current. We have the own height, but do we have the right max? When we are traversing from left to right, let's say if I am at this element, do I have the right max for this element? I don't have it, right? Because to have it, I will have to see all these elements and know what is the maximum among these. So there is some problem. We cannot have left max and right max both calculated during the iteration using the variables like previous and current. We will have to store at least one of them in the whole array, like we'll have to declare a new array and store a right max for all of these elements in that array, and then we can iterate from left to right, and then we will have the left max own height as per the iteration, and for the right max we will refer to that array. So what does our final algorithm look like? We first declare a right max array. We fill it as we saw in our previous slide in big O of n time. We also declare a previous left max variable because we are not filling the left max array. We are only using the variables. That way we will have to fill one less array. We will use some lesser space. So we declare a previous left max variable with its value as A0. We also have total water, which will track the total water trapped so far in the iteration. And then we iterate from left to right. What all do we have in each iteration? We have a previous left max value. We have a right max of I from step 2. We have the own height or AI. Now we can calculate the current left max using the previous left max and AI. Then we can calculate the water by element because now we have the current left max, we have the current right max, and we have the own height. We can now add it to the total water. And finally, we can update the previous left max to current left max because it will be used in the next iteration. Finally, we return the total water. Now, what will be the time complexity of this algorithm? It will be big O of n because we are iterating only once here, and in previous iteration we just filled the right max array. The space complexity will also be big O of n, but we are filling only one array, right max array, and not the left max array. Let us now see the working code for the same algorithm that we discussed. You can also find the link to this code in the description. There is a small change here. In the algorithm, we stored the right max array and we calculated the left max using current and previous variables. While here, we have done the opposite. But the process and logic remain same, so you should be able to do it either ways. So here, first we declare the left max array. Then we fill the left max array. There is a method that we have called for it. Then we declare two variables, the right max, which is current, and the right max for previous. Then we have a total water variable that tracks the total water calculated. Now we iterate here from right to left. Now first we calculate the current right max using the previous right max and the current element. Then we calculate the water by this element using the current left max, current right max, and its own height. Then we add that to total water, and then we update the previous variable to the current so that it can be used in the next iteration. And we return the total water. Let's just see the few functions that we have used. First method is to calculate and fill the left max array. We start with first element and then we iterate from left to right, and left max at I is equal to math.max from left max at I minus 1 comma the current element. And similarly, to calculate water by element, it is the same formula that we discussed. We calculate the minimum of the left max and right max, and we subtract own height from it. Let us now see an extension of the same problem. Our current solution takes big O of n space complexity because we have to store at least one array, either left max or right max. Can we make it big O of 1? Basically, can we find a solution where we don't have to store either the left max or the right max? Let's see. The problem was that when we were traversing from left to right, at that time we had not seen the right elements for that particular element. So we needed right max in an array. And similarly, when we were traversing from right to left, we needed left max in an array. Since we need left max and right max, we have to traverse in both the directions at once, maybe using two pointers, let's say I and j. Now, if there was some way that I could calculate water at either of these elements, then in every iteration I would be able to progress at least one of these pointers. And till the time all of these pointers, both of these pointers meet, I will have water calculated at every element. So here we are not filling it left to right, We are not filling it right to left. We are filling it in both the directions, but in one iteration, only one of the element gets filled and only one of the pointer gets moved. Let's see if we can do this. Now, I have traversed from left for iterator I and I have traversed from right for iterator j. So for position I know what is the left max so far, and for position j, I know what is the right max so far. Now either of them will be smaller and either of them will be bigger, right? So let's say when my I and j are at this position, let's say left max was smaller. Now can I calculate water at element I? Water at element I is determined by left max, right max and own height. I know own height. I know left max also, but I don't know right max for I. But does it really matter? What I need is minimum of left max and right max. And when I am saying that left max right now is lesser than the right max, that means the right max for I will always be greater than the left max. Therefore, I only need the left max and own height here to calculate water at I. So I can calculate the water at I and move the I pointer forward. Similarly, if it was greater, let's say if right max was smaller here and left max was greater, that means for j, I would know the own height of j, but I would also know that since left max is greater for j, that means minimum of left max and right max for j will be right max, and I can calculate the water at j. So the key insight that we are using here is that we don't actually need the left max and right max values for an element. What we need is the minimum of the two for a particular element. We don't care if we don't know the actual right max for element I. What we only need is that, hey, the minimum of the two for element I will be left max and we know its value. So what will our approach for the extension problem look like? We will have two previous variables, one for left max and one for right max. We will also have two pointers I and j, one to iterate from left to right and one to iterate from right to left. Now in every iteration we have the previous left max, previous right max, we have our AIs and AJs. Using that we can calculate the current left max and current right max. Now we will compare the two. Now if left max is smaller, that means for ith element, right max will always be greater or equal than the current right max. So the minimum of left max and right max will always be left max. So we can calculate the water at element I. We can also increment the I pointer and we can add that to the total water. Similarly, if left max is greater, then we can calculate the water at j, we can increment j pointer and we can add it to total water. Then we can update our previous variables using the current ones and we can finally return the total water. This now makes our space complexity also as big of 1 because we did not have to store anything. To summarize, we first understood the problem with an example. Then we could see that the total water we can calculate by calculating water stored at every element and then summing it up. Now to calculate water stored at every element, we saw that we needed a maximum value to its left, maximum value to its right. We needed to take minimum of the two and then subtract its own height from it. That will be the water stored at that particular element. Our subproblem now became that how do we calculate left max and right max for any element. We saw an efficient way or a big O of n time way to calculate that for every element. For that, we used the value of the left max for the previous element to calculate the left max of the current element and similarly for the right max. Therefore, we could now have the left max and right max. But we needed extra space to store the array left max and right max. We further observed that we actually only need the previous element to compute the left max for current element. Therefore, we can optimize on space as well. But then we tried to apply this solution, this learning to our problem, and we tried iterating from left to right. We could see that we can have the left max calculation done in the iteration on the go using the variables previous and current, but we don't have the right max for it. Therefore, we had to store right max in an array, and our algorithm became a big O of n time complexity and big O of n space complexity. We did a code walkthrough for that. As an extension to the problem, we tried to solve it in big O of 1 space. We noted that it is not necessary that we have to traverse either from left to right or from right to left. We can have 2 pointers and we can traverse from 2 directions simultaneously. Now, if at any point in time, let's say left max at I is less than right max at j, then obviously right max at I will also be greater than or equal to left max at I. Therefore, we could see that minimum of left max and right max for element I will always be equal to left max, and therefore we can calculate the water stored at element I and we can progress the pointer. But if left max would have been greater than right max at I would have been greater than right max at j, then we would have calculated water at element j. This is it for this video. We will meet again in the next video with some other problem. Thank you for watching.